Continuation from last time. Are there any questions on how we got to these resonance forms? Why this is now the major product? Or any questions about that? Looking at, remember our trends in bond formation: negative nucleophilic carbon, negative charge, to a positive carbon. That's how the bond formation works there. Okay, so we're going to do a few more examples here for Diels-Alder, just to wrap up our discussion there, and then we will touch upon some other stuff as well. Just a second. Thank you. All right, so let's do another example of Diels-Alder here. So just to summarize, how to tell if you have Diels-Alder, what's the major product, just to summarize here. Okay. So let's do another example. All right. All right. So this is S-trans conformation here. Okay. So we have our diene. It's not in the right conformation yet. And our alkene here. So our diene and our dienophile. Okay, so if you heat this up 100 degrees Celsius in toluene. So toluene is a benzene ring with a methyl group, and that's used commonly as a solvent. And then, like I was saying the other day, this is commonly found in paint thinner and gasoline. Okay, so all right, since this, in the dienophile, since the groups are trans, you have a trans alkene, you'll have a trans product right here. So these will be trans, and then you could get the enantiomer as well. But usually this group here, this is where the group will line up. So you'll line up based on the electron withdrawing group here, being situated towards that end. Okay? Yes,
Does
Catherine.
it matter which groups we select that are the same as, like, which ones together are both cis and which ones are similar? I mean,
Yeah, so actually, I don't think it actually, it won't matter because you actually form the other enantiomer as well. So it's racemic, so you don't have to worry about that. Just write one or the other. So you can write this like cis or trans. So don't worry too much about that. Okay, but you'll get this structure here. And I want to, again, reiterate, how do we get to this stereochemistry? Okay, so I'm just trying to explain how we get to the stereochemistry at these positions. How do we get to this stereochemistry, and this stereochemistry? Okay, so the S-trans isomer will isomerize to the S-cis. So we want to draw it like this. Like that. Okay. Okay. So when people write this in textbooks, they usually have to make things clearer, they usually represent a few of these bonds a few different ways, okay? So this bond right here, this methyl group, should be a dash bond because usually the groups that are pointing outside, they are dashed, okay? And the ones coming out towards the inside here, this hydrogen, that's considered a wedge bond. So I'm going to draw those in right away, okay? And then let's look at these wedge bonds right here. I'm going to highlight this to indicate that it's pointing out directly from us to make it a little perspective drawing, okay? So here's the double bond. All right. Now this bond is going to be approaching the alkene here. And remember, the alkene will orient this way based off the resin structures we kind of just referenced over here. Okay, so for the diene, for the diene there, you would want to situate it right there, yeah. So here we have more partial positive character at this carbon. So that's why it's partially positive there, okay? And at this position, it's more partially negative and partially positive here, okay? And then here would be partially negative. And the reason I draw these partial charges is based off how I drew these resin structures previously. They're based off those charges right there, okay? All right, so remember in endo, our endo selectivity here, the H on the alkene are going to point away from the diene. And so the methyl group here has to point away as well because it's trans to the electron withdrawing group. So the electron withdrawing group, that interaction with the diene is going to drive this reaction forward. Okay, so and then this hydrogen goes right here. All right. All right. So I want to annotate this a little bit. So look at this hydrogen, and this group right here. So these two groups right here, they look at that central alkene. I don't have a ruler, sorry. So this central alkene right here, right? So see this double bond? These two bolded groups, the bolded single carbon-carbon bond and the bolded hydrogen, they are cis to each other. So these two groups are cis. That's a cis double bond, okay? And then here, if we look at this H here, so look at this H in a different color. This H and this group here, all right, they are trans to each other. Trans to each other. All right. So this hydrogen, so the group that's part of the diene, that's kind of cis to the carbon-carbon single bond, that group is pointing in opposite directions. The H is going this way, and then as the alkene approaches, the acetyl bond group is approaching under the diene and is pointing in the opposite direction. So those groups are trans to each other. So in the endo transition state, that is actually what happens as this reaction proceeds. So here now we're drawing the two bonds that are going to form there, and you're going to get this structure right here. The major product here. So these groups are typically, oh, my bad. We're supposed to draw another bond. I apologize. So here. So, right. So put a carbon right here, guys. So put a carbon there. And that's where this carbon shows up in the product. Okay? So the groups that are on the outside, so see how the ethyl group is pointing towards the outside? The hydrogen is pointing towards the inside of the region of the diene. That's where we get the wedge and dashed stereoselectivity. Okay? So this group is going under the diene, so it's going to be situated below. So that's why it has a dash bond. And then this methyl group, it's trans to the electron withdrawing group, so that's why we draw it wedged right here. Okay. So this next stuff, this is just information to kind of explain why this happens. Okay. So the easiest thing to do is say, okay, let's just not talk about that. But that's not telling you the whole story. Okay, so you have the right to know why this happens. Like, why do we learn this? And the reason is it's a powerful reaction. Okay, so here's the summary for predicting. So this is the endo product. So endo product. So how do you know? How do you write how do you know if it's endo or exo? All right, so there's this little chart that actually helps you guys. Okay, so let me just write a little description here. Let me just say right here. So that's my example. So here's the summary. Here is a little summary for the Diels-Alder reaction. All right, here's your diene, and we're going to put the groups here. All right, this group is situated to the outside. This group is situated on the inside, like that. Okay, so here, O is outside. I is inside. Okay, so then your question is like, okay, if I have my dienophile, how do I know if it's exo or endo? Okay. So if your groups are situated on the outside as the dienophile approaches, that's your exo position. Those groups are exo in the Diels-Alder product. They are exo, that's the exo adduct, okay? Now, if your groups are situated in the inside, those are endo, right here. These will be considered endo, okay? So when your alkene approaches, the side, the substituents that are on the endo side, the left-hand side of the diene, so I guess it's important that you draw it this way. The diene on the left, the alkene on the right. So when you approach, the groups that are on the left of the alkene, they are going to be situated endo. So this is the little cheat sheet we have to kind of explain that selectivity right there. Okay, so this doesn't make much sense right now, so let's do an example to kind of illustrate how we would know. Do I have an example here? I thought I did, so no. Okay, this one, I didn't know. Okay. Okay, I think I did. All right, give me 1 second. No, all right. Thought I had so much stuff. I guess it's not important. All right. Okay. So let's say I have this diene right here, and I have my electron drawing group. Like this, okay? Set that. All right. So, hold on, let me see where I'm at here. Okay. All right. Okay. So, you have two potential products here, okay? So, let's draw the ring. All right. So, if you have these groups, these methyl groups, if they are the opposite stereochemistry of your substituents on the dienophile, this is the exo adduct. All right, so see here, they are wedged here. This is the exo adduct. Now, if I have these substituents on, they are cis to the groups on the exterior, right here. See, I have this adduct. This is endo. Okay, so that's my process here. You look at the groups that are outside and inside, okay? So, when I was drawing this here, so let's put, sorry, this is a little messy, this arrow here. So this is what the product would look like, okay? So let me just show you this. Boom. All right. So the exo groups, the outside groups, okay, would be dashed. The inside groups are going to be wedged, okay? And then if you have an exo group, the exos will be wedged. And then the endo groups are dashed, okay? So this is the relationship between endo and exo. The endo groups are on the same side as the outside groups, and vice versa. The exo groups are on the same side of the inside groups, cis to the inside groups, but trans to the outside groups. That's how the Diels-Alder reaction works. The endo groups, the things that are positioned endo, are trans to the inside groups, cis to the outside groups, and that's why I wrote it like this. In the exo, they are trans to the outside groups. Endo, they are cis to the outside groups. So that's the main difference between endo and exo. Now, do I really require you to write this on be able to explain it this way or predict this kind of stereochemistry? No. So what I expect you is to draw the product of a Diels-Alder reaction and explain to me, be able to identify that, oh, okay, my dienophile should have electron withdrawing groups on it, CN groups, CO2, R groups, and then my diene should have carbon releasing groups. So these type of groups. R groups here, these methyl groups here, or electron donating groups, such as, where was it? Let's go up a bit. Sorry. These type of groups. These groups. Those type of groups. Those are electron donating. When you have a oxygen right next to a pi bond, electron donating. Okay? All right, so that's the Diels-Alder. We're going to go over one last thing for Diels-Alder, and then we will be done with chapter 14. Okay, are there any questions about endo or exo? This is explaining the complexities of Diels-Alder. So stereochemically, there's a lot to consider, but it doesn't take away from the utility of this. You could form a six-membered ring and incorporate all the atoms. So that's the usefulness of this. So example of synthesis, I might say, okay, here's a ring structure. Predict how you can make this ring structure. Can you retrosynthetically say, okay, this ring, all right, so this ring right here, this ring, I broke this bond, and there's a double bond here. I broke that bond, and I get to these two groups. Can you retrosynthetically say, okay, that came from these two groups? So I can propose that I use these two starting materials. These two starting materials are pretty common. You can buy them. I can use that to do a Diels-Alder, just add heat, and I get this ring structure. And then from there on, I can say, okay, well, you can't stop there. You need to convert maybe this CN group or this ketone or aldehyde, convert to alcohol, use, maybe a Grignard reagent or lithium aluminum hydride, sodium borohydride to make the alcohol. That's like the extra step I will probably do. I won't probably do any more than that because that would be a bit too much. So that's kind of like where synthesis is going towards. The highlight is what we learned. The main focus, the main reaction is using a reaction we learned previously in the two chapters, but then there might be some additional steps you have to do just to get to the final product, okay? But it won't be crazy. You don't have to take like 3 alkene reactions, maybe it's just 1 alkene reaction to get maybe a dibromo compound, like in the quiz, but it won't be crazy like, some of the things you probably saw, maybe you look in the textbook. Those are a little bit more tricky, but I want the elementary concepts first, okay? So I'll focus on that. All right, but for Diels-Alder, I want you to be able to say, okay, go from the 2 starting materials and be able to form the ring structure, okay? And for stereochemistry, all you should remember is that if they're on the same side of the dienophile, they should now be cis in the product. And they are, in fact, cis in the product. Okay? And if they are both pointing outside like this, they must be in the same geometry, so they're both cis. The 2 methyl groups are both cis as well. Okay? And I kind of outlined that in my little notes there for the diene. All right, so there's one last thing we have to talk about. This is purely for academic purposes, okay? So you might be wondering, why does this even happen in the first place? Okay? So let's talk about MO Deary. of Diels-Alder. All right. So remember, like I said, all of chemistry is all reactions happen because you have polar reagents, polar stuff reacting with polar stuff, and sometimes you have nonpolar stuff reacting with nonpolar stuff, okay? So most reactions can be explained by just using first principles of opposites attract, okay? But there comes a time when these reactions don't have charges, only in the resin structures they do. Okay? So how do these reactions form anyway? So reactions either form from opposite charges attraction of that nature, or like we try to explain as best as we can when orbitals overlap. So when orbitals overlap, they can engage in the chemical transformation. All right. So here's your diene and this dienophile. So I'm going to explain why. Why the endo product is so favored. Okay, so here's my dienophile. I have an aldehyde bonded to an alkene there. Okay, so I have, in each of these cases, I have 4 pi electrons. I have 4 p orbitals interacting with each other. Okay, so if you have 4 p orbitals interacting, when you draw molecular orbitals, you're going to have 4 different molecular orbitals for each case. So pi 4, pi 3, pi 2, and pi 1. Okay? So let's draw the easiest one, the pi 1. That's the bonding molecular orbital. Everything is filled. There are no nodes. So 4 p orbitals in sync right here. All right? So and then for the diene, we have 4 electrons filling the lowest 2 energy orbitals. Okay? As we go up in energy, remember, I'm not sure if you guys learned this. So remember you have the 1s orbital. As you go up to the 2s, 3s, 4s, we start to get areas in the orbitals where electrons cannot be found. You guys remember what that's called? Starts with an N. Say again? Close. So we call them nodes. So there's regions of density where there's nodes. But yes, anti-bonding orbitals have nodes, okay? So when we go over here, okay, we have the 4 orbitals again, but as you go up in energy, the number of nodes, the number of dotted lines has to increase by 1. So here, and it has to be symmetric. So the orbitals have to be symmetrical. So I have to split down the orbitals where I have an equal set on each side. So 2 orbitals on each side, and they're opposite signs. So that's called a node. Okay. Then when we get to the third set of orbitals, they have to be broken down symmetrically and change sign at least twice. So that's why I put these 2 dotted lines. There are 2 nodes here. We have a line there, and then these must be in sync. So that's the third molecular orbital for this diene. And then when we have the 4th orbital here, we must have nodes in between pretty much every orbital here. So now we have signs changing on all 4 of them, okay? And this picture will look exactly the same for our dienophile. Pi 4, pi 3, pi 2, oops. So let's recopy what we drawn on the left side. So 4 orbitals here, all in sync. They have all the same sign, so that's a bonding interaction, okay? This one also has 4 electrons because there's 2 pi bonds right here, 1 and 2. 1 and 2 right there, okay? Now this one again, 1 node, so we're going to split the orbitals like this. in the third orbital like that, okay? So I don't expect you to draw these orbitals. This is merely to help explain why this reaction happens. This is the more complete picture. You can't use resin structures for everything, unfortunately. All right, so you see all these here, they all orbitals that match, okay. So these set of orbitals, we can call them the LUMO, the lowest unoccupied molecular orbital. So that's the lowest energy orbital that's not occupied. And then these ones, pi 2, those are the HOMO bonds, so the highest occupied molecular orbital, okay? So what you do here, what happens in the Diels-Alder is you're going to use you're going to draw the diene here, okay? So sorry, this is the dienophile. Right here. All right, so let's draw our diene. So I'm going to do this the best I can. Okay, so for the dienophile, so this is our dienophile, we're going to use the LUMO of dienophile. So look at this picture right here. This is the orbital picture we're going to use, okay? So what happens here is that we're going to use this picture. Okay? So see how the p orbitals are kind of aligned here? And you see that they have different shadings to indicate that only a particular orbital of the other reactant can interact with it. Okay? So that's the LUMO of the dienophile. Okay? Now, this one here, we use the highest occupied molecular orbital of the diene. Okay, so we use the diene here. Okay? So what happens here, if we look at the HOMO picture here, the diene is this one, okay? So we're going to draw those two groups right here. So two of the bonds are similarly shaded, and then two of the other bonds are not as shaded. Whoops. Okay. So what two orbitals are affected here? All right. So did I draw this correctly? Oh, my bad, guys. Let's backtrack. All right, let's flip this one. Sorry about that. So this one should actually be shaded right there, okay? So the LUMO here, if we look at the LUMO, yes, sorry about that. Okay. Now let's look at where the shadings overlap, okay? So this bond can overlap with that because they're on the same sign, okay? So these orbitals can't interact unless they have the proper symmetry or the same sign of the orbital, okay? So symmetry here refers to like the orbital, the shadings here, and like the sign of the orbital, okay? So they have to be the same color in order to overlap. So this one can interact with that one, and that's where the major bonding event forms. And this one is going to interact with this one, and see here, these two positions, right? These two positions are the primary orbital overlap. So that's the major bond forming event. So that's how the Diels-Alder works. But why is this endo state preferred? Look at the double bonded O. It's towards the diene. Why is that favored? Well, there's another interaction here that helps stabilizes it. So the closeness of this orbitals is what helps stabilizes the endo transition state. So this interaction is called the secondary orbital overlap. Okay, so in the endo transition state, okay, so this secondary overlap in the endo transition state stabilizes the transition state. So it's these interactions that stabilize the transition state. But what happens here, there's no bond formation, okay? So no bond formation occurs here. This interaction is merely to stabilize that transition state. So that's why this product, the endo product, forms. And when you have something similar, let's draw the exo transition state. So when you draw the exo transition state, I'll ask you a question. Why you think this one is not as preferred? Okay, so you have those orbitals here. Oh, sorry, I forgot to draw the methyl groups. Okay. Now, if we draw the exo transition state, the oxygen group is situated away from the diene, so it's pointing further away. Okay, so we have this situation here. Okay, so again, the same type of interactions are present for the bond forming, this interaction. Okay. Oh, sorry, my bad. Wrong bond. All right. So this one is interacting with this bottom lobe. And this bond is interacting with this lobe right here. So those are where the major bond forming events happen, right? That alkene is interacting with both of these double bonded alkene p orbitals. Okay? But look at here. Look at the exo transition state. Where is this oxygen pointing? Is it anywhere near the other orbitals to stabilize it? Right here. So if we kind of look at this position, right? This oxygen can't, look at right here. So if we compare this position to, if we think about this position and we compare it to this position where it's stabilized in the endo transition state, it's too far. So this secondary overlap is not possible. Okay, so the pi orbitals, or the pi orbitals or the p orbitals are so far away they can't reach it. So that's why this transition state is no longer. This transition state is higher in energy. It's less stable, and that's because this electron withdrawing group can't help stabilize it in the endo. So even though endo, the two groups are more sterically crowded, it's actually that this stabilization here is that's enough to cause it to be the product that forms the fastest, even though it's not the most stable. So this is the kinetic product, and the exo is the thermodynamic product because it's the more stable of the two, even though it forms more slowly. Okay, so that is the explanation of Diels-Alder. So thanks for sticking with me for that one. Yes, Catherine.
I'm confused with the higher up with the little levels that you showed with like pi 1, pi 2.
Yes.
Why is that the diophene, even though on like the orbitals that we drew it, is at pi 3?
Oh, okay. So when you have two orbitals that bond, you have to have one orbital that's empty to accept the electrons. So that forms the bond, right? And then one orbital has to be the electrons that are being donated. So it's like a Lewis acid base. Lewis base donates electrons to an atom that can accept them. So one of those orbitals that we use to bond here. So this is called frontier molecular orbital theory. So the rationale behind this is that one orbital is unpopulated, and that will accept the electrons that form the bond. And that's the LUMO of the more electron deficient molecule or reactant. So we used pi3 here for the LUMO, for the dienophile, and that matches this guy right here. So we need like an empty orbital and a filled orbital. That makes the greatest stable. That's the best bond making orbitals to use. So that's why we use that one.
And then would LUMO and HOMO be the same for the diene?
No, so for the diene, we actually use the highest occupied orbital.
Okay.
Right here. So you need something filled with electrons and then something that lacks electrons in order to be shared and form a bond.
But the HOMO would still also be pi2, right?
Yeah, it's pi2, yes. So it's still considered pi2. So we're using the HOMO over here, the pi2. It's still the same one, yes, for both cases. Now, sometimes the diene will just have one pi electron or two pi electrons. So sometimes the levels can differ. But in this case, we're using the same, it looks like the same molecular orbitals, but we're using the LUMO of the dienophile. So that's the empty orbital. That's the higher energy orbital. It's lower in energy because of the electronegative atoms. And we're using the HOMO there from the electron donating diene because that's the highest in energy. So when the orbitals are closest in energy, you get the most stabilization. Okay, but that's the molecular orbital theory. You don't really have to reproduce this, but that's the background behind what causes the bonding in this case. Okay, so the last thing I'll talk about is these reactions for this chapter. Intramolecular cycle addition. So the last class of reactions here that we'll cover on this topic. So Diels-Alder is one type of this reaction. Intramolecular cycle addition. So these are called, sorry, I can't spell. Electrocyclic reaction. So electrocyclic means the electrons are moving in a ring. So there are other type of reactions that looks like Diels-Alder, okay? All right. So the funny thing about these reactions that you can push it one direction and then push it in another direction by just using a different heat source, okay? So you can actually close this ring if you just heat it, okay? So how does this happen? Well, just like in Diels-Alder, everything moves in a ring, so this is what happens. Boom, boom, boom. So when the p orbitals are so close together, you get these weird reactions where this ring will just close, okay? So this is electrocyclic reaction where ring closure is favored. So this ring closure gives you negative 14.5 kcals per mole. So that's a very favorable reaction. So we could say ring closure in this case is favored. Is favored, okay? All right. Now you can go backwards to favor the more unfavorable reactant by using light. So using light of a certain wavelength. So heat will favor the more stable product. When you lose light, you can actually form the more less stable product. So it's a little interesting there. And the other classic type here is a cyclobutene. So what do you think is wrong with this molecule? You think it's particularly stable? If you just look at it. What's wrong with cyclobutanes in general? They suffer from what? Ring. Bond angle strain, right? So that's part of ring strain, right? So all the angles in there are not great. And then there's a lot of, remember torsional interactions from rotation. So not, or, like groups eclipsing interactions. So not the best, right? So this wants to just break free. All right, so here we have a very strained ring. Okay? Like that. So this ring can open quite readily. So what happens here is you have two bonds moving here to break the ring open, and you create a diene now. So this is very favorable, 9.7 kcals per mole. Okay? So ring opening is favored. Okay? All right. So now, if you try to do the reverse reaction, see, so we know that the forward direction to form this is very favorable. But if you try to use this, start with this and heat it, you might think, okay, can't we just go backwards? No, you get no reaction. Okay? So here, cyclobutene is unstable. Okay? So what heat does, heat controls the reaction by forming the most stable product. So that is controlled by thermodynamics. So that's why this reaction is not favored to go. However, you see what I wrote in this arrow? What did I wrote here? This reaction could go backwards as long as I use what? No, not heat. This one is for heat. Sorry, that was not clear. So this one's going to this product with heat, but what about I go reverse? I'm using a light source. So remember in Gen Chem, you excited the gas and it gave off a certain color, right? Like you use hydrogen gas, you looked at it, you put electricity, it gave it a different color. So you promote it to an excited state. So the interesting thing about light is we can promote electrons to an excited state, they can react, and you can form a product. So here, light. So this won't work with heat, but light or photochemical reactions, that's where light is used to drive a reaction forward. They can form unstable products by excitation. So by exciting a molecule. So what happens here? You go to a higher energy state. Okay. And then what happens here? It relaxes. Okay. And then what happens here? You can form the more unstable product. So you can actually get back to the other product by using light. So it has to do with these energy states here, okay? So say here, we just to wrap this up here for this chapter, say you have your molecule here. Here's your molecule. So this is my molecule. My molecule is this group right here. All right? We know if we hit it with heat, it won't do anything. So let's just excite it with a photon. So what happens here when I get a photon? What happens to this molecule? What is it going to do? It sounds like physics now. So what happens when the molecule gets a photon of light? That molecule now has enough energy. And what does it do? Say again? Yeah, quantum leap or quantum jump. So we make a quantum jump to the excited state right here. All right, so now we go to our excited state. Okay, now we're in the higher energy level. Okay? So now at this molecule here, when it's in the excited state, it has enough energy to rearrange, its bonds can vibrate, it can rearrange to the product. So it's in the metastable state. Okay? So here I could say molecule reacts, and we get to our product. Our product here was the cyclobutene ring, like that, okay? Now, once that molecule has formed a product, it's going to not be stable, so it's going to jump back down right here, releases that same photon of light that it absorbed, and now you have converted to the product, okay? So sometimes the energy will be used to rearrange. You go to the product, you relax back down, so it relaxes here, and you get to the unstable product. So the unstable product can form. Okay? So that's how photochemistry works. I know it sounds weird, but it's like contradictory to what you think. Why would something more unstable form? Well, if you're in an excited state, you can pretty much do anything because you have a lot of energy. So that's what happens. Rearranges to the product. Now it can go back down, relax, and you form the product. So that's the genius way how we use light instead of heat to drive a reaction forward. And some reactions, they just work that way. All right, so this here is trying to explain that, Diels-Alder is just a subset of cycloadditions. So that introduces you to kind of like all the kind of reactions Diels-Alder can do. Okay, and that's the end of this chapter. Are there any questions of that one? Okay, so what should you take away from this? Be able to, the practice exam, it tells you have some reactions with NBS, remember that allylic position. And then when you have dienes, be able to draw the kinetic versus thermodynamic product when you have a diene reacting with HBr or HI or HCl, okay? So you get 1,2 addition or 1,4 addition. And those problems were covered on the practice exam, and you saw some examples in your notes, okay? And the other part you should take away, thermodynamic product, kinetic product, and then the other thing is Diels-Alder. If I gave you 2 reactant molecules and you see heat there, or sometimes there's light for Diels-Alder, but usually it's heat because it drives the reaction forward. When you see that, you should HV or heat, you should think Diels-Alder. When there's 2 diene and an alkene present, think Diels-Alder, okay? Drawing that product. And if you have stereochemistry involved, think about the relative stereochemistry, okay? And then use the quiz to review the alkyne reactions and how to use that in synthesis. That will help you. I think that will be pretty helpful. And then the synthesis problems on the practice, those are meant to be a little bit challenging, okay? So the best way is to think, okay, what groups are added to my synthesis and what reactions do I need to add those groups? And the only way to get practice with this is to do some practice synthesis problems, okay? So hopefully those ones on active and the ones, the practice problems like some in the book, please use those to practice, okay? But use the practice exam to kind of guide you, okay, I need to review synthesis a little bit more here, all right? And then lastly, you can expect an NMR type problem. Maybe I give you the formula, okay, and I gave you some spectra. Or maybe I say, okay, I did a series of reactions. I don't know what this material is, but I got this product and this product. But like active, can you suggest the structure of the starting material? So you might have the NMR with you, the IR, and maybe carbon NMR to help you aid in your description. But you also might have reactions present to help you kind of guide you to that process. So please still review NMR. You can expect NMR type problems to be on all the future exams, okay? Because NMR is an important part of how we analyze molecules, and we'll see this a lot too, analyzing spectra in lab as well, okay? So NMR is an important part here for just studying chemistry in general. That's like the go-to for reactions. Okay. All right. We have a few more minutes here, 20 minutes. We're just going to start talking about benzene, okay? But are any other general questions before I move into chapter 15? No, remember, none of this stuff we covered today. This theoretical background, and I just explained more about Diels-Alder because it's a huge reaction. There's been like many studies on it, okay? Different flavors of it. You could just dedicate a class to just Diels-Alder, like, not just a class, but maybe like a maybe a third of a semester to it. So it's a pretty big field there, and it's still being studied today. It's still very widely used. Okay, so chemists use it all the time. So it's an interesting molecule. Okay, but any other questions on chapter 14, the Diels-Alder reaction? So if you use a study guide, I kind of go over like each reaction you should know. Okay, so use that to kind of help you guide your study. And then use the practice exam to see how you do on those reactions. Okay, that'll be a big part. All right, any other general questions? Okay. All right. All right. Okay. Now this is chapter 15. All right. So this chapter and the next chapter will cover benzene reactions. So we talked a lot about benzene, but we never really talked about what it's all about. Okay, what is benzene? Why is it so important? Why is this compound and all? Why is it like all these other compounds? Okay, so unlike cyclohexane, benzene has a lot more reactions it can undergo. Okay, so don't worry too much about chapter 15 yet. We probably won't think about this probably until next week when we talk about the next upcoming quiz about it. Okay, but aromatic compounds. Let's just introduce the topic. So first, there is a bunch of nomenclature we have to be familiar with. And with benzene, it's pretty simple. The nomenclature is a lot simplified based on what we know about the other nomenclature. Okay, so benzene ring. The easiest thing about benzene, as long as it doesn't have an alcohol, or I won't say that. For the most part, naming benzenes are easy because most of the time, naming a benzene is the parent name is benzene, and you have substituents on the benzene ring. Okay, so for example, how would we name this? We have a benzene, but the first position will get bromo. 1 bromobenzene. Okay, 1 bromo. Then we have 2, 3. What do we have there? Yes, dimethyl. Dimethyl benzene. So when you have no alcohol, you have no carboxylic acid, no amine. It's pretty simple it's pretty straightforward to name these compounds here. Okay. All right. Let's go over some more. All right. Some of these compounds, I will just list their common name because their IUPAC name has been supplanted by their common names. All right. So we have an alkene and an alkyne and a benzene. So even though you have an alkyne and an alkene, the benzene is 6 carbon long. So that takes precedence. So here, this will be a benzene. All right. So remember, if we have an alkyne and an alkene on the same parent compound, and you can give them the same number depending on which way you number the compound, the alkene will get precedence. So here, it'll be 1, ethanol. Okay, and then 1 here, 2, 3, 4, 5, 6. 1 ethanol, 3, sorry, no, we can't name it that way. Why don't we name it that way? Okay. Interesting. Okay. So, let's go backwards. All right. I have to check this out, but basically it's this, 4, 5, 6. And, oh, I think I know why. I think I know why it's this way. All of these carbon groups are 2 carbons long, so I think it's purely alphabetical, okay? 1 ethanol, then 3 ethyl, and then 5 ethinyl. Okay, so if we compare the alphabet here, we have ethanol, then Y here, and then the Y here, there's an N versus an L. So that's why ethyl comes first, okay? So in this part, it's purely alphabetical. Benzene takes precedence, but now it's based on the alphabet of the substituents, as long as it's not an alcohol, okay? And then the parent name here at the end is benzene, so it's still benzene, okay? All right, so let's go over some other ones. All right. So this is called methylbenzene. You don't have to specify the number. Methylbenzene. All right, so this common name is toluene. All right, does anyone know what toluene is used for? Yeah, gasoline. So it's a solvent, right? Good. So it's present in gasoline. It's added as an additive to help the mixture burn more efficiently. So that's a solvent. All right, good. Now here, when we take the benzene and we add a vinyl or alkene group, the simplest alkene group here, we get this structure. So this is called ethanol benzene. Okay, so the common name for this is called styrene. All right, does anyone know where styrene is from? When you think of styrene, what kind of product do you think of? Styrofoam. Yeah, so packaging materials like peanuts, packaging peanuts, styrofoam based, materials to keep your stuff safe in transport. So this is a major component in not just a chemical industry, but manufacturing products. So styrene. So this is called. So this is involved in polymer manufacture. All right. So that's an important compound there. So styrene there, a very important compound used extensively. In making polymers. Okay. All right. Now we get to carbon-based atoms. So not carbon-based, but we have different functional groups here. So here, when we have an oxygen and a CH3 group, okay, that is called medoxybenzene. However, this is known by a common name. That's called anisole. All right, so be familiar with the common name. That's kind of how we'll relate to it. So that's anisole. What is anisole used for? Well, this compound in particular, when it reacts, it's used to form perfumes. All right, so some of your perfumes may have this compound in it as like a scent. So it's used as perfumes. Okay? All right. Now let's get to substituted benzene. So when you have a 1,2, so there's a common substitution pattern. So the most common ones we'll see is di-substituted, right? When benzene has 2 substituents, okay? When it's 1,2, we call it 1,2-dimethylbenzene. Okay. The shorthand we call this we use the word O. So that stands for ortho. O-R-T-H-O. And then this particular benzene, we have a common name for it. That's called xylene. So orthoxylene, okay? So this is also a solvent. Okay? So when we have di-substituted benzenes, okay, there are common substitution patterns we'll see. So when it's 1,2 di-substituted, it's called O. We use the prefix O. That stands for ortho. 1,2 is ortho. Okay. When it's 1,3 di-substituted, we have a different letter. That's called M dash. That's called meta. All right. That's the meta position. Now, when it's on opposite sides of the ring, 1,4 di-substituted, that's called, that we give it the prefix P dash, that's called para. So in the future, I will refer to benzene compounds when they're di-substituted. I'll say it's the ortho product, the meta product, and the para product. And that refers to these substitution patterns. 1,2, 1,3, and then 1,4. Okay? So that's something to look ahead to in the coming the next thing we work on. Okay. All right. So that's the di-substituted methyl. So orthoxylene if it's 1,3, metaxylene, then paraxylene. So there's different isomers that are used in the chemical industry. Okay. All right. Now here, interesting flavor. All right, benzaldehyde. When we have an aldehyde, we call it benz, and then the aldehyde group takes precedence. So aldehyde. So starting next week, I will give you guys a handout about all the naming priorities. So you know, okay, this has a higher priority than this, because now we're going to talk about carbonyl groups, and then we have to see which is the order. Is a carbonyl higher than an alcohol versus an alkene? So there's a whole list we're able to consult and say, okay, it's going to be higher. I should name it this way. All right, so benzaldehyde, that's the flavor of almonds, but it's actually an artificial almond flavor. So it's present in almonds, but it's not the actual flavor of it. Okay, so you can read about it. It's an artificial almond flavor. It has a particularly almondy scent. Okay, so it's a very sweet scent, but in high concentrations, it might be a little too much, be a little too strong, but it has a sweet kind of almond smelling scent. So that's benzaldehyde. So benzaldehyde, I think also used in food products, so it's used for that artificial kind of flavor and smell. All right. Next thing we can have is a ketone here. This ketone smells somewhat sweet, but don't let that fool you, because this compound is used as a hypnotic drug. So maybe it's used to kind of provide some relief, especially if you're maybe mentally strained or stressed there. So acetophenone, it does have I have worked with acetophenone. I actually made it before. It does have a sweet kind of aroma to it. Hypnotic kind of tendencies there. Okay. All right. So has anyone ever worked with phenol? So phenol is the benzene ring with an OH group. So the thing about phenol, you gotta be careful. Phenol, if you get it on your skin, it will readily absorb in the bloodstream. And if it's too high of a concentration, it could be deadly. So you gotta be careful when working with phenol. Don't spill any on your clothing. If you do, take it off right away. Jump in the shower. You gotta get that stuff out of your system because it'll readily absorb through the skin and through the bloodstream there, and it could get into your system. So you gotta be careful. So we call this the proper name is benzenol. So benzene plus alcohol, benzenol. And alcohol has precedence, that's why we call it there. But the more common name we call this is phenol. Phenol or phenol. So we've seen structures like this when we talk about alcohols. So much of the chemistry is very similar. This is, however, used as an antiseptic. So disinfect, not just simply disinfecting, but as a precaution against sepsis, okay? Anesthetic, so to knock out the pain, okay? And then sometimes, didn't know about this, using sore throat sprays as part of that kind of concoction there. The kind of, treat a sore throat. I've never seen it in like the products I would use, but that's apparently what it is in, okay? All right, so we have different kinds here. Ketone, we have a ketone group here, acetophenone, aldehyde, and then did I do benzoic acid? Oh, not yet, okay. So let's talk about two more, okay? One with a nitrogen ring. All right, so this compound, we'll talk more about this compound later, but the chemistry here, this is called aniline. So the common name is aniline. I think the formal name is either aminobenzene or benzamine, maybe? Benzamine. But I think it's aminobenzene is one of them, or aniline, that's the more common name. So when you refer to this group, we usually just call it aniline, okay? What aniline is used for, I guess I should mention this, dyes, and a more serious note, fentanyl. Or carfentanil. You can make it from aniline, actually. So that's like one of the starting materials. All right, but anyway, lastly, let's talk about the acid version of the benzene. So we have an acid molecule on here. All right, so this is used heavily in the food industry. This is called benzoic acid. All right, so this chemical is found in food preservation. So if you ever look on your food packaging, your sodas, it'll say something benzoate, sodium benzoate. It's that molecule in the conjugate base form. It's used as a preservative. So it fights off your food going bad. So instead of your food going bad, I think this thing kind of forms a protective layer around it. It has an aroma, very strong sweet aroma, so it's used in foodstuffs, okay? So that's a food preservative. But it kind of makes you wonder, like, how safe are these things really? Maybe we should look more into that. I don't know. That's just my 2 cents. Okay. So that's so these are all the kind of derivatives benzene can make, and they have you see all these uses here, very wide range uses as not just a chemical, as an ingredient, okay? So one is benzene though, a substituent, and when is it the primary chain, okay? So let's talk about just 2 more things here. As a substituent, C6H5 is named phenol. All right. So if you have a parent chain, there's a benzene ring on there. As a substituent, you name it as phenol. It's like phenyl bromide, bromobenzene. All right. So as a substituent, it's phenol. Now, if you have a benzene ring, and it's bonded through one carbon atom. This looks very similar to an allylic group, one carbon over from the double bond. So you have one carbon over from the double bond. So this is called benzyl. So these are two names we'll have to be familiar with. Phenyl and benzyl. So when it's directly attached to the ring, use phenyl. When it's attached to a CH2, then a benzene ring, we have to use the word benzyl there. Okay? All right. So, as practice for naming these things, all right, let's go over here. All right, this one. Which group do you think gets priority? The acid or the amine? Yeah, the acid. So more oxygens, higher oxidation state, acid. So this gets our priority. All right. So this is the one position, 2, 3, 4. So when that has priority, the amine is a substituent, 4-amino. So that's when we have nitrogen as a substituent, amino. And then what's the parent name for benzene and an acid? What acid did we just go over here? Benzoic acid. So we use the parent name of that one. So this would be benzoic acid. Okay. So let me use an example where it's not the parent name. Okay. And this will be the last thing we do, I promise. All right. So with alcohols, what is the parent chain? It has to contain the alcohol, right? So let's just circle the parent chain, okay? This is the parent chain. Now let's number the parent chain. 1, 2, 3, 4. All right, that's it. So even though the benzene has more carbons, you do not name it as a benzene. So at the 4 position, we're naming it as a substituent for phenyl. And where's the alcohol in this case? 2. So 2-butanol. All right. That's the nomenclature for benzene. All right. So for the exam, don't worry about this stuff. Focus on the stuff we did last Thursday for 14, 13. And to use that to prepare for Thursday. Okay, guys? Good luck. And let me know if you have any questions. I will have office hours, tomorrow and then Thursday right before the exam from 10 to 12 p.m., okay? So good luck. And if there's any questions, let me know. Post them on Campus Wire. Remember, you can get extra credit on Campus Wire as well.